Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with the Mars shadow mystery, solving the 50-year Martian shadow. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. The Mars shadow mystery emerged from decades of observations, igniting curiosity among astronomers and scientists alike. This phenomenon, first noted during the early explorations of the red planet, involved peculiar shadows that seemed to drift across its surface, prompting speculation regarding their origins. Initial interpretations ranged from natural geological formations to the possibility of ancient Martian life. Historical missions, such as Viking in the 1970s and the more recent rovers, expanded our understanding, yet the shadows persisted as an enigma. These spacecraft gathered invaluable data, revealing intricate details of the Martian landscape, but the shadows continued to elude definitive explanation. Each new observation added a layer of complexity as researchers grappled with varying hypotheses. The phenomenon gained prominence in scientific literature and public discourse, leading to collaborations among international space agencies. These efforts highlighted the importance of interdisciplinary approaches, combining geology, atmospheric science, and astrophysics to tackle the riddle. Over the years, theories evolved, with some proposing that these shadows were cast by transient atmospheric conditions or dust storms, while others speculated about the influence of seasonal changes. Each hypothesis drew on the wealth of data collected, underscoring a collective pursuit of clarity amidst obscurity. The shadows, elusive yet persistent, beckon deeper exploration into the Martian environment. Early observations of Mars began in the 17th century, when astronomers first turned their telescopes toward the heavens. These primitive instruments revealed the red planet's distinct hue, prompting curiosity about its surface and atmospheric conditions. The clarity of their observations was limited by the technology of the era, yet they noted shifting features, suggesting a dynamic landscape. In the 19th century, advancements in optics led to more detailed studies. Observers like Giovanni Schiaparelli documented what they believed to be canals, igniting speculation about potential life forms. These interpretations shaped public perception and scientific inquiry, fostering a desire for further investigations. The intrigue surrounding these observations laid the groundwork for a deeper understanding of Martian phenomena. The 20th century brought significant improvements in observational capabilities, with the introduction of larger telescopes and sophisticated photographic techniques. Astronomers began to map the surface, capturing the variations in color and brightness that hinted at geological diversity. The arrival of robotic missions, such as Mariner 4 in the mid-1960s, marked a pivotal shift, providing the first close-up images of Mars. This initial phase of exploration revealed a world of extremes, characterized by vast plains, towering volcanoes, and deep canyons. Each observation contributed to a growing body of knowledge, inviting more questions about the planet's past and its potential for hosting life. The Martian atmosphere, although thin, reveals a complex interplay of gases and particles, composed primarily of carbon dioxide. It contains traces of nitrogen, argon, and oxygen, alongside water vapor and various other compounds. This unique composition influences surface conditions, dictating temperatures that fluctuate dramatically between day and night. Dust storms frequently sweep across this region, engulfing the planet in a hazy veil that can last for weeks. These phenomena are driven by the interplay of solar heating and atmospheric dynamics. Solar radiation warms the surface, which in turn heats the air above it, creating convection currents. These currents can lift dust into the atmosphere, allowing it to be transported vast distances, altering visibility and atmospheric pressure. The low pressure of the Martian atmosphere, less than 1% of Earth's, results in a reduced capacity to retain heat. This characteristic leads to significant temperature drops during the night. In this environment, large temperature swings occur, presenting challenges for any potential life forms that might have existed. The lack of a magnetic field further complicates the atmospheric landscape, exposing it to solar winds and cosmic radiation. This exposure has contributed to the gradual erosion of the atmosphere over millions of years, reshaping the planet's surface and leaving behind a barren landscape marked by ancient riverbeds and mineral deposits. Whispers of a wetter, more hospitable past. Understanding the interaction of light and shadows in space reveals fundamental principles of physics that govern planetary atmospheres. Light, emanating from the sun, travels vast distances, illuminating celestial bodies and casting shadows that delineate their features. On Mars, the angle of sunlight varies dramatically with the seasons, influencing the shadows cast across its rugged terrain. This phenomenon assists in the analysis of surface topography and atmospheric conditions. Shadows on this planet provide insights into the height and texture of geological formations. The interplay between the sun's position and Martian topography leads to pronounced contrasts, allowing scientists to infer the dimensions of cliffs, valleys, and craters. The shadows serve as tools for measuring not only physical depth, but also the potential for past water flow, revealing the planet's climatic history. Variations in shadow length and intensity across different regions are affected by atmospheric density. In the thin Martian atmosphere, shadows can appear sharper and more defined, accentuating the starkness of the landscape. These shadows can even reveal seasonal changes, as the shifting sun alters the contour of light and darkness across the surface. This examination of light dynamics contributes to a broader understanding of Mars's past, enabling researchers to construct models of its atmospheric evolution and further unravel the mysteries of its shadowed features. Early theories regarding Martian shadows emerged during the initial explorations of the planet in the late 19th century. Observers noted the elongated shadows cast by various geological features, leading to speculation about the nature of the Martian landscape. Theories ranged from the existence of vast canals formed by intelligent life to the implication of drastic topographical variations resulting from geological activity. These interpretations reflected the limitations of the observational tools available at the time, which often led to whimsical conclusions. Advancements in technology throughout the 20th century allowed for more detailed observations. The introduction of high-resolution imaging and spectroscopy led to a more nuanced understanding of shadow formation. Shadows were increasingly recognized as indicators of elevation changes and surface texture, rather than signs of artificial structures. The identification of shadow patterns aligned with geological formations enabled scientists to hypothesize about erosional processes and sediment deposition on Mars. Investigations into the relationship between shadows and the planet's atmospheric conditions provided insights into the interplay of light and surface materials. Such studies underscored the importance of shadows in discerning the Martian climate's fluctuations over time, revealing the potential for past water activity and its impact on the surface. This evolving perspective underscored the significance of Martian shadows as essential components in reconstructing the planet's geological and climatic history. Advancements in telescopic technology during the 20th century marked a pivotal shift in the capacity to observe celestial phenomena. Enhanced optics and sophisticated sensors allowed for unprecedented clarity in imaging distant worlds. The introduction of radio telescopes expanded the spectrum of observation, revealing insights that optical instruments could not capture. These advancements facilitated a deeper understanding of Martian features, enabling scientists to detect subtle variations in surface composition and atmospheric dynamics. In this era, the advent of space-based observatories eliminated atmospheric interference, providing an unobstructed view of Mars and the surrounding cosmos. High-resolution imaging uncovered intricate details of the Martian surface, including craters, valleys, and polar ice caps. As technology progressed, the ability to monitor seasonal changes on the planet became possible, leading to new hypotheses about its climate evolution. Digital imaging techniques transformed data collection, allowing researchers to analyze Martian shadows with remarkable precision. This capability unveiled the interplay between solar illumination and topography, highlighting the shadow's role in understanding temperature fluctuations. The comprehensive data acquired through these technological advancements paved the way for future missions, further enriching the narrative of Mars. The combination of refined instrumentation and innovative methodologies positioned scientists to delve deeper into the Martian landscape. The Viking missions, launched in the mid-70s, marked a pivotal moment in the exploration of Mars. These ambitious undertakings aimed to uncover the planet's secrets, including its geological and atmospheric characteristics. Equipped with sophisticated cameras and scientific instruments, they captured detailed images and data that would shape understanding for decades. Observations of the Martian surface revealed unique features and formations, some of which prompted intrigue regarding their origins. Among these discoveries were the vast plains and the towering volcanoes, visible through the lenses of the orbiters. Their ability to analyze shadows cast by surface formations provided insights into the height and scale of these geological features. The shadow observations were instrumental in estimating the topography, revealing the intricacies of the terrain. These measurements contributed to a greater comprehension of the planet's history, hinting at past volcanic activity and erosion processes. Vikings landers, equipped with analytical tools, conducted experiments on Martian soil, searching for signs of life and studying the atmosphere. This dual approach, orbital imaging and surface analysis, established a foundation for future exploration. The interplay between these early missions and their findings continues to resonate, guiding current and future endeavors aimed at unraveling the enduring mysteries of Mars. The significance of shadow within planetary mapping cannot be overstated. Shadows provide critical information regarding surface features, revealing variations in elevation and texture that may otherwise remain obscured. The precision of shadow analysis relies heavily on the angle of light, which can be manipulated through various imaging techniques. One such technique involves the use of high-resolution cameras mounted on orbiters. These instruments capture images during different times of the day, enabling scientists to examine shadows cast by geological formations. This process, known as photogrammetry, allows for the creation of three-dimensional models of the Martian landscape, offering insights into its geological history and potential past conditions. Additionally, radar altimetry serves as a complementary tool in shadow studies, measuring the distance between the spacecraft and the surface. This data helps quantify the height of features like cliffs and craters, enhancing the understanding of Martian topography. The interplay of these tools culminates in a more comprehensive view of the planet, revealing intricate details hidden within the shadows. Althea, As the study of shadow continues to evolve, the integration of artificial intelligence and machine learning algorithms further enhances data analysis. These advancements allow for the rapid processing of vast amounts of imagery, ensuring that even the faintest shadows are meticulously examined for the clues they hold about Mars and its complex geological past. The polar ice caps of Mars play a significant role in the formation of shadows across its surface. Composed primarily of water ice, these regions exhibit seasonal variations that influence the surrounding landscape. During periods of increased sunlight, sublimation occurs, causing the ice to transition directly into vapor, which alters surface albedo and subsequently affects light reflection. This process creates stark contrasts in brightness that contribute to the shifting patterns of shadows. The intricate interplay between sunlight and these ice caps results in a dynamic shadow landscape, particularly noticeable during the Martian summer. Shadows elongate and shift, revealing unique geological features that might otherwise remain hidden. As the ice recedes, it exposes underlying materials, which may include ancient regolith and potential signs of past water activity. Such features can provide invaluable information regarding the planet's climatic history and its ability to support life. Shadows cast by the ice caps highlight these geological formations, drawing attention to their significance. Analyzing these patterns allows researchers to reconstruct the environmental conditions that prevailed in Mars's past. The study of shadow formations, thus, becomes a crucial aspect of planetary science, offering insights into the processes that have shaped this red planet over eons. Understanding these phenomena enhances the broader narrative of Mars's evolution. Dust storms frequently sweep across this region, obscuring visibility and altering the landscape in profound ways. Seasonal shifts on Mars often trigger these storms, transforming the atmosphere into a hazy veil that can extend for hundreds of kilometers. The increased particulate matter diminishes light's penetration, impacting the shadows cast upon the Martian surface. During these storms, shadow visibility fluctuates dramatically, leading to a complex interplay between light and dark. In the midst of a dust storm, shadows may appear muted or entirely obscured, rendering previous measurements and observations nearly impossible to interpret. Scientists have noted that the duration and intensity of these storms can vary widely from one Martian year to the next, sometimes lasting for weeks. This variability complicates the study of shadows, as researchers must account for atmospheric conditions that are not only unpredictable but also transient in nature. The interplay between dust and shadow challenges the understanding of Martian geology and climate dynamics. Amidst this swirling atmosphere, the faint remnants of ancient geological formations emerge, hinting at the planet's storied past. These formations, shaped by past winds and perhaps by water, become shrouded in mystery as dust storms sweep across the surface. The challenge lies in discerning the enduring features beneath the ephemeral veil of Martian dust. The Mars shadow hypothesis arises from the need to address fundamental questions surrounding the observed phenomena. The first inquiry considers the nature of the shadows that have persisted for decades, seemingly unaffected by Martian meteorological shifts. Understanding the origin of these shadows demands an examination of the planet's geological history, inviting speculation regarding ancient volcanic or tectonic activity. Investigations into the composition of the Martian surface provide further insight. The mineralogical makeup, influenced by aeons of cosmic events, prompts questions about the processes that shaped these enduring features. Are they remnants of long-extinct geological formations, or do they signify ongoing activity beneath the surface? The interplay between solar illumination and Martian topography introduces another layer of complexity. Variations in sunlight angle during different seasons could potentially reveal hidden characteristics, illuminating areas of interest previously obscured. This relationship between light and shadow guides researchers toward potential discoveries, and exploration of atmospheric conditions is essential in this context. The thin Martian atmosphere, rich in carbon dioxide, interacts with dust and other particulates, complicating visibility. How these conditions affect shadow perception remains a crucial aspect of the inquiry. These questions converge into a singular focus, directing scientific endeavors aimed at uncovering the truth behind these Martian shadows and their implications for the understanding of planetary evolution. Spectroscopy serves as a vital tool in Martian studies, allowing scientists to analyze light reflected from the planet's surface and atmosphere. This process reveals the composition of soil, minerals, and potential organic compounds, providing insights into the environmental conditions that have shaped this region. By examining the spectral signatures emitted or absorbed by various materials, researchers can infer the presence of water ice, carbonates, and other essential substances. Shadows cast on the Martian surface become an additional layer of investigation through this analytical lens. Variations in light intensity and color can indicate differences in texture and composition within these darkened areas. The interaction of sunlight with the Martian atmosphere further complicates this analysis, as dust particles and gases scatter and absorb light, altering the perceived colors and intensities. Understanding these shadows is critical in identifying past geological processes, such as volcanism and erosion. The shadows may also hint at the presence of subsurface features, where light fails to penetrate deeply, creating areas of unknown composition. This information can illuminate the history of water on Mars, guiding future missions aimed at exploring potential habitats. As the quest for knowledge continues, the examination of light and shadows remains a cornerstone in unraveling the mysteries that lie within the Martian landscape. The advancements in understanding Martian shadows have been significantly aided by the contributions of rovers such as Opportunity and Curiosity. These sophisticated machines have traversed vast distances across the planet's surface, gathering invaluable data. Their cameras, equipped with high-resolution imaging technology, capture intricate details of the terrain, allowing for the analysis of light interaction with various geological formations. Opportunity, operational for nearly 15 years, provided insights into the planet's ancient environments. Its exploration of Meridiani Planum revealed evidence of past water activity, aligning with the variations in shadow lengths and angles observed in the region. The rover's meticulous documentation of these phenomena has led to a deeper comprehension of the interplay between topography and solar illumination. Curiosity, continuing the legacy, has explored the Gale crater, which presents a unique geological history. The rover's ability to analyze the composition of rocks and soil has unveiled layers that reflect different eras of Martian climate. The shadows cast by the towering Mount Sharp have been particularly revealing, showcasing how the sun's position alters perceptions of the landscape. Together, these rovers have transformed the understanding of Martian shadows from mere curiosities into critical elements in deciphering the planet's past. Their findings underscore the intricate relationship between light, shadow, and the geological narrative written across the Martian surface. The interplay of Martian seasons significantly influences shadow length and direction. Each season, lasting approximately 6 Earth months, alters the planet's axial tilt and orbital position, resulting in variations that define the landscape. During the northern summer, sunlight penetrates deeper, casting elongated shadows that stretch across the rugged terrain. Conversely, in the winter months, shadows grow shorter and more defined, accentuating the contours of craters and geological formations. This cyclical change not only affects visibility, but also impacts temperature fluctuations and atmospheric conditions. As sunlight becomes less intense, the surface cools, leading to the formation of frost and the seasonal migration of carbon dioxide ice. These phenomena contribute to the shifting appearance of the Martian landscape, revealing dormant features that might otherwise remain hidden. Measurements taken over several Martian years provide a detailed record of these shadow dynamics, allowing scientists to map the changing environment with precision. Observations highlight the importance of understanding shadow behavior in discerning the historical climate patterns of Mars. These insights contribute to the broader narrative of planetary evolution, illuminating how ancient processes shape present-day features. This ongoing research continues to uncover the mysteries of Mars, offering a glimpse into the complex interplay between celestial mechanics and planetary geology. The effect of Mars' axial tilt on shadow behavior reveals intriguing patterns that contribute to the understanding of the planet's environmental dynamics. With an axial tilt of approximately 25 degrees, similar to Earth, this inclination influences seasonal changes. These variations directly impact the length and orientation of shadows cast by topographical features across its surface. Observations highlight how shadows shift dramatically with the changing seasons, creating a cyclical rhythm that reflects the planet's axial orientation. During summer months in either hemisphere, shadows shorten and become more pronounced, while winter months elongate them, leading to a stark contrast in appearance. The interplay between the sun's position and the planet's topography results in fascinating visual phenomena, including the potential for significant temperature gradients influenced by this tilt. The unique Martian landscape, characterized by valleys, craters, and towering volcanoes, presents a vast array of shadow forms. Each feature interacts differently with sunlight, revealing the nuances of Mars's geological history. This interplay provides insights into atmospheric conditions, as temperature variations can influence dust and debris movement across the surface. The study of these shadows not only aids in mapping the terrain but also enhances understanding of Martian climate patterns, forging a deeper connection between sunlight and surface evolution. Through ongoing exploration and data collection, the Martian shadow continues to unveil the mysteries of its past. The interplay between topography and shadow patterns significantly shapes the understanding of the Martian surface. Valleys and mountains create complex landscapes that influence how shadows are cast and perceived. In elevated regions, shadows stretch across vast plains, revealing the contours and depths of the terrain. This phenomenon allows scientists to map the topography with greater precision, as the length and angle of shadows indicate the height of surrounding features. In lower-lying areas, shadows can become intricate, often obscuring subtle geological formations. These regions may house ancient riverbeds or volcanic remnants, their outlines softened by the diffused light. Shadows can highlight these features, revealing evidence of past climatic conditions and geological processes that have long shaped the planet. The effects of seasonal changes also play a role in shadow dynamics. As the sun's position shifts throughout the Martian year, shadows change in length and intensity, offering insights into the planet's axial tilt and orbital patterns. This cyclical variation enhances the understanding of Martian climate history and its evolutionary trajectory. Each valley and mountain contributes uniquely to the shadow patterns observed. By analyzing these variations, researchers can piece together a more complete picture of the Martian environment, forging connections between its geological history and current atmospheric conditions. The exploration of these shadows remains an essential aspect of unraveling Mars's enigmatic past. Theories surrounding shadow anomalies suggest a complex interplay between terrain features and atmospheric conditions. Investigations into these phenomena reveal an array of unexplained features that challenge conventional understanding. Distinct formations appear under specific angles of sunlight, casting elongated shadows that stretch across the Martian surface. These peculiar shapes often defy straightforward geological explanations, prompting scientists to explore various hypotheses. Some propose that the shadows originate from unique geological structures. The presence of towering cliffs, vast mesas, or peculiar spires may contribute to the intricate patterns observed. Others theorize that subsurface activity, such as tectonic shifts or volcanic processes, could create transient features that alter shadow behavior over time. These variables complicate the task of establishing a definitive source. Atmospheric conditions also play a crucial role in shadow formation. Fine dust suspended in the thin Martian atmosphere can scatter light, affecting how shadows are cast. This scattering effect could result in illusions where features appear more pronounced than they are. Observations from orbiting spacecraft and rovers provide critical data to support these theories, as high-resolution imagery allows for close examination of shadow anomalies. Continued analysis of this intricate relationship between surface features and atmospheric conditions may eventually yield insights into the planet's geological history and its potential for hosting life. Computer simulations have become essential tools in the quest to unravel the complexities of Martian shadows. By modeling the interactions between sunlight and the planet's varied terrain, researchers can simulate the formation and movement of shadows across the surface. These simulations provide a framework for interpreting the high-resolution imagery captured by orbiters and landers, allowing for a more nuanced understanding of the underlying physical processes. The intricacies of Martian topography, including its craters, valleys, and ridges, significantly influence how shadows manifest. The simulations account for these features, incorporating variables such as atmospheric density, dust distribution, and solar angles. This comprehensive modeling enables scientists to predict shadow behavior under different conditions, enhancing their ability to analyze real-time observations. Stein by the Zielfinch and refinement of these simulations improve their accuracy, providing a clearer picture of how shadows change over time. By correlating simulation results with empirical data, researchers can identify patterns and anomalies that may suggest geological activity or atmospheric variations. This computational approach not only aids in understanding the current state of the Martian surface, but also contributes to broader discussions surrounding its climatic history. Insights gained through these simulations can help inform future missions aimed at exploring potential habitats for life, revealing the delicate interplay between light and shadow on the red planet. Data gathered by the Mars Reconnaissance Orbiter has ushered in a new era of shadow analysis, providing unprecedented detail about the Martian surface. This spacecraft, equipped with high-resolution imaging systems, has captured thousands of images, illuminating the enigmatic patterns formed by shadows cast across the terrain. These images reveal subtle differences in albedo, surface texture, and topography, contributing to a deeper understanding of how shadows influence temperature, and potential moisture retention. The analysis of these shadows extends beyond mere visual appeal. They serve as indicators of seasonal variations, highlighting changes in surface conditions that may affect habitability. Areas previously deemed inhospitable are re-evaluated, as shadows can signify locations where water ice persists beneath the surface, potentially supporting microbial life. Additionally, the data allows for the identification of recurring shadow patterns, suggesting geological processes that shape the landscape over time. Sand dunes, craters, and cliff faces are reshaped by wind, and their shadows tell a story of the planet's dynamic environment. This information is crucial for upcoming missions which aim to gather samples and conduct in situ experiments. The intricate relationship between light and shadow on Mars not only shapes our understanding of its geology, but also informs strategies for future exploration, ensuring that efforts to uncover the planet's secrets are grounded in precise, data-driven insights. The Cheruvin Insights. The shadow cast by Olympus Mons, the largest volcano in the solar system, stretches across vast expanses of Martian terrain. This colossal shield volcano, towering approximately 13 miles, exhibits a unique topography that has intrigued scientists for decades. Its expansive slopes create a gradient of light and dark, accentuating the geological features that reveal the planet's volcanic history. The shadow is not merely an absence of light, but a phenomenon that influences temperature variations in this region. During the Martian day, the sun's position alters the characteristics of this shadow, providing insights into the thermal dynamics of the surface. The cooler regions beneath the shadow create microclimates that may harbor unique geological processes. These conditions may play a crucial role in understanding how volcanic activity has shaped the planet over millions of years. In addition to the geological implications, the shadow of Olympus Mons holds significance for future exploration. Robotic missions may utilize this natural phenomenon to study the underlying composition of the volcano and its surrounding environment. Investigations into the shadow's impact on surface materials could yield valuable data regarding the potential for past or present microbial life. Continued analysis of this shadow enhances the broader understanding of Martian volcanism, paving the way for deeper inquiries into the planet's transformational history. The interplay between Martian climate and shadow dynamics reveals significant insights into the planet's atmospheric conditions. Seasonal variations on Mars lead to fluctuations in temperature and pressure, influencing the distribution of shadows cast by prominent geological features. These shadows can alter microclimates, creating localized environments that differ markedly from surrounding areas. Observations indicate that regions in perpetual shadow exhibit reduced temperatures, which can affect the stability of surface ice and influence the potential for liquid water formation. The presence of shadowed areas provides a unique opportunity to study how these microenvironments contribute to the overall climate system. Areas sheltered from sunlight experience different thermal cycles than those exposed to direct radiation. This variation impacts dust movement, with shadows acting as barriers that trap sediments and alter the regolith composition. Understanding these dynamics is crucial for assessing how climate changes over time may have influenced surface processes and the potential for habitability. Data gathered from rover missions and orbiters continues to refine this understanding. It sheds light on how shadows interact with atmospheric phenomena, such as dust storms, which are prevalent on Mars. These interactions may shape surface morphology, and affect the distribution of resources necessary for future exploration or even colonization. The relationship between climate and shadow dynamics. The Curiosity rover's findings have provided significant insights into the shadow phenomena observed on Mars. Data collected over numerous sols has revealed how shadows shift and stretch across the Martian landscape, influenced by the planet's unique axial tilt and atmospheric conditions. Measurements indicate that during specific times of the year, shadows can elongate dramatically, creating patterns that hint at underlying geological features. These patterns suggest that shadow interactions may reveal hidden structures, such as the remnants of ancient riverbeds or volcanic formations. The rover's imaging systems, equipped with high-resolution cameras, have captured images that show how shadows can obscure or highlight features that would otherwise go unnoticed. Temperature fluctuations also play a crucial role in understanding these shadows. At dawn and dusk, the temperature gradient on the Martian surface can lead to atmospheric refraction, causing shadows to appear more pronounced. The rover's thermal sensors have noted these variations, enabling scientists to correlate shadow intensity with temperature changes. Further analysis of these findings may offer insights into past environmental conditions on Mars, aiding in the reconstruction of its climatic history. This understanding not only enhances knowledge of Martian geology, but may also inform future exploration missions aimed at unearthing the secrets of the planet's surface and the possibility of past life. The interplay of dust on Mars plays a crucial role in shadow formation, influencing optical effects that shape perceptions of the landscape. Fine dust particles suspended in the thin atmosphere scatter sunlight, creating an array of visual phenomena. This scattering results in various shadow intensities across the Martian surface, leading to optical illusions that can mislead observers regarding distances and dimensions. Dust devils, a common occurrence in this region, also contribute to the dynamic nature of shadows. These swirling columns lift particles from the surface, temporarily altering the distribution of dust in the atmosphere. The resulting fluctuations in shadow intensity can provide insights into the local weather patterns and surface conditions. The implications extend beyond mere aesthetics. Understanding how dust influences the appearance of shadows may assist scientists in interpreting geological formations and stratifications. Variations in shadow lengths and depths can indicate the relative heights of surrounding terrain and the contours of ancient riverbeds. This knowledge becomes increasingly vital as missions venture closer to the surface, where accurate assessments of the environment are paramount for robotic and human explorers. Precise navigation depends on deciphering these optical effects, ensuring that the shadows cast by Martian features reveal their true nature rather than concealing it beneath layers of dust. Temperature variations significantly influence shadow analysis on Mars, altering the behavior of light and the visibility of Martian terrain.
This region experiences extreme fluctuations, with daytime temperatures soaring to approximately 20 degrees Celsius, while nighttime can plummet to nearly -100 degrees Celsius. Such disparities affect the atmospheric density and the way light interacts with dust particles suspended in the thin air. Farksun Alexid and Sana hundreds Haitas casts shadows that can obscure or enhance surface features. Thermal changes prompt the movement and settling of fine particles, leading to shifting patterns in illumination. Shadows, therefore, become dynamic elements, revealing more than mere shapes. They indicate temperature gradients, which in turn inform scientists about the composition of the surface and subsurface materials. These phenomena are vital in understanding the geologic and climatic history of the planet. For instance, varied shadow lengths can hint at the presence of ice or hydrated minerals beneath the surface, as they interact differently with temperature fluctuations. In the polar regions, shadows may linger longer due to the presence of frost and ice, hinting at seasonal changes. The interplay of temperature and light not only illuminates the Martian landscape, but also aids in the quest to decode its past, offering insights into the processes that shaped this enigmatic world. Such analysis is essential for future exploration and potential habitation. Examining the Martian moons reveals significant insights into the shadow effects that influence the planet's surface. Phobos, the larger of the two, orbits at an astonishingly close distance, completing a full revolution in just over 7 hours. This rapid orbit leads to unique shadow patterns that shift dramatically throughout the Martian day. The elongated shadow of Phobos, cast across the rust-colored terrain, accentuates the undulating surface features, creating transient areas of darkness that can alter local temperatures. Deimos, smaller and more distant, presents a contrasting shadow profile. Its slower orbital period results in subtler interactions with sunlight. The shadows cast by Deimos are more diffuse and linger longer, providing a gentle dimming effect on the Martian landscape. Observations of both moons contribute to the understanding of their gravitational interactions with Mars, affecting tidal forces and geological stability. The study of these shadows not only reveals insights regarding surface conditions, but also plays a role in understanding solar radiation exposure on potential landing sites. The interplay of light and shadow fosters a complex environment that may influence future missions. By mapping these effects, scientists can better predict how Martian weather patterns will respond to the cycles of its moons, guiding efforts in exploration and habitation for the years to come. The interaction of light and dust in this region creates a complex interplay that influences visibility and temperature. Dust particles suspended in the Martian atmosphere scatter sunlight, resulting in a phenomenon known as dust storms. These storms can envelop vast areas, reducing solar radiation reaching the surface. Such conditions contribute to the planet's notorious cold temperatures. The frostmas to approximately 20 degrees Celsius. This scattering also plays a role in the visual phenomena observed on Mars. During dusk and dawn, the sun's position relative to the dust particles presents a unique spectacle. Shadows elongate and distort, creating an almost surreal landscape that shifts in hue and tone. Observations during these periods reveal the subtle variations in atmospheric density as the shadows deepen and shift in response to the changing light. Data gathered from orbiters and rovers have documented these shadow effects across various locations. In the northern plains, the interplay of light and shadow reveals the diverse topography and geological history. Dust devils, spinning vortices that lift fine particles into the atmosphere, contribute to localized shadow patterns, further complicating the understanding of Martian climate systems. In essence, these interactions not only affect the immediate environment, but also influence broader climatic trends, impacting future explorations aimed at understanding this enigmatic planet. The study of light and dust remains crucial in unraveling the complexities of Mars. The shadows cast by Martian canyons offer a unique window into the planet's geological history. Valles Marineris, the largest canyon system in the solar system, stretches over 4,000 kilometers and reveals intricate layers of sediment. These formations, created through millennia of erosion, provide evidence of ancient climatic conditions. The interplay of sunlight and these towering cliffs leads to varying shadow lengths, which shift dramatically with the sun's position. Measuring these shadows enables scientists to infer the height of canyon walls and analyze their structure. In the early morning, the elongated shadows stretch across the canyon floor, revealing hidden features that may otherwise remain obscured. As the day progresses, shadows recede, exposing the vivid colors and textures of the Martian surface. This cycle of light and dark is not merely aesthetic, it serves as an essential tool in geological mapping. In Valles Marineris, the analysis of shadows contributes to understanding the potential for water flow in the past. Patterns within these shadows can indicate where water may have once pooled or flowed, suggesting the presence of a more hospitable environment. Observations of these dynamic interactions continue to refine our understanding of Mars' climatic evolution and its capacity to support life. Each canyon casts a story waiting to be deciphered, revealing the planet's hidden past. In geological studies, shadows play a crucial role in understanding the landscape's features. The interplay of light and shadow reveals the subtle topography and intricate details of Martian formations. Variations in shadow length and intensity provide essential clues about the elevation and depth of structures. This phenomenon is particularly significant in regions where sunlight reaches at a low angle, accentuating the contours of the terrain. Observations from orbiting spacecraft have demonstrated that shadows can highlight features such as crater walls, ridges, and the edges of valleys. Measurements taken from these shadows allow scientists to compute the height of cliffs and the depth of craters with remarkable precision. The interplay of sunlight and these geological formations unveils the complex processes that have shaped the Martian surface over billions of years. Additionally, the study of shadows aids in determining the composition of surface materials. Variations in color and texture illuminated by sunlight can be analyzed in conjunction with shadow patterns to infer mineralogy and identify potential resources. As researchers delve deeper into this phenomenon, it becomes evident that shadows are not mere absence of light. They are integral to constructing a comprehensive understanding of Mars's geological history. Through these observations, the Martian landscape emerges as a dynamic canvas, revealing the ongoing evolution of a planet that continues to captivate curiosity and exploration. The integration of artificial intelligence into the analysis of shadow data marks a significant advancement in planetary science. Advanced algorithms process vast amounts of visual information captured by orbiters and landers, identifying subtle variations in shadow patterns that may indicate geological features or atmospheric conditions. This technology facilitates the extraction of insights that were previously obscured by the sheer volume of data. Machine learning models are adept at recognizing intricate patterns, allowing them to discern the nuances of Martian terrain. For instance, they can identify shadow lengths and angles with remarkable precision, which can then be correlated with topographical features like cliffs, dunes, and craters. Such analyses can elucidate the processes shaping the surface, from erosion to sediment deposition. The continued refinement of these tools enhances predictive capabilities, fostering a deeper understanding of seasonal changes on Mars. Shadows can reveal the shifting behaviors of dust storms, the formation of frost, or even the presence of transient water ice. The findings generated through artificial intelligence not only support ongoing missions, but also guide future explorations, directing focus toward regions of high potential for study. This evolving partnership between artificial intelligence and planetary science underscores the transformative potential of technology in unraveling the mysteries of Mars. The insights gained pave the way for a more profound comprehension of the planet's past, present,
and potential for life. Shadows on Earth and Mars present unique characteristics that illuminate the underlying differences in their respective atmospheres and geological features. On Earth, shadows shift and morph with the sun's apparent movement across the sky, revealing the dynamic interplay of light and surface. The Earth's atmosphere scatters sunlight, creating softer edges and varied intensities. This phenomenon allows shadows to encompass a spectrum of hues and depths, influenced by atmospheric conditions, topography, and vegetation. Mars demonstrates a contrasting behavior. The thin atmosphere results in sharper, more defined shadows with pronounced edges. Light does not scatter as extensively, leading to stark delineations between illuminated and dark areas. These shadows can provide critical information about the terrain, revealing subtle variations in elevation and surface composition. The planet's rocky landscapes, including vast plains and towering volcanoes, accentuate these features, highlighting the contrast between sunlit and shadowed regions. Both planets exhibit shadows that reveal aspects of their geological histories. On Earth, shadows can indicate the presence of water through features such as riverbeds and valleys, while Martian shadows often reflect the remnants of ancient volcanic activity or erosion patterns, hinting at a once dynamic environment. By examining these shadows, scientists glean insights into the processes that have shaped both worlds over eons, contributing to the broader understanding of planetary evolution. Variations in Martian shadows reveal the planet's dynamic history. Observations over decades have shown how these silhouettes shift, providing a record of geological activity. Erosion, sediment deposition, and volcanic events contribute to the changing landscape, altering the way light interacts with these ancient structures. This region exhibits distinct patterns that suggest the flow of winds and the movement of dust, which play a vital role in shaping the surface. Notably, the interplay of shadow and light on Martian terrain has changed due to seasonal cycles. During the colder months, surfaces freeze, creating hard formations that cast sharper shadows. As temperatures rise, thawing initiates a transformation, revealing softer edges and blurring the outlines of these formations. Such subtle changes over time are pivotal in understanding climatic shifts on Mars. Data collected from orbiting spacecraft provides a continuous timeline, enabling researchers to construct a detailed narrative of Martian evolution. Each shadow captured reveals not just the physical characteristics of the landscape, but also hints at the atmospheric conditions that prevailed at different epochs. These insights help scientists piece together a comprehensive picture of how Mars has evolved, informing theories about its past and guiding future exploration missions aimed at uncovering its secrets. LiDAR has emerged as a crucial tool in shadow detection and analysis on Mars. This technology utilizes laser pulses to measure distances and create detailed topographical maps of the planetary surface. By sending rapid bursts of light towards the ground, it captures variations in elevation and surface features with a remarkable precision. This capability allows researchers to identify the subtle distinctions between illuminated and shadowed areas, revealing important geological structures. In the context of the 50-year Martian shadow phenomenon, LiDAR data enables scientists to monitor the shifting patterns of light and shadow across diverse terrains. It provides insights into the changes in surface albedo, which can vary due to geological activity or the presence of dust. The ability to generate three-dimensional representations assists in understanding how shadows interact with surrounding landscapes, influencing the thermal dynamics of specific regions. These analyses are not limited to surface studies alone. LiDAR facilitates the exploration of subsurface features, uncovering hidden formations that may contribute to the planet's enigmatic history. By integrating LiDAR observations with other remote sensing data, a more nuanced understanding of Martian geology and climate emerges, allowing for targeted investigations in future missions. This methodical approach underscores the significance of advanced technology in unraveling the complexities of our neighboring planet. Investigating the influence of solar activity on Martian shadows reveals a complex interaction between the sun's emissions and the planet's atmospheric conditions. Variations in solar radiation can lead to fluctuations in temperature, affecting the density and composition of the thin Martian atmosphere. This, in turn, modifies the way shadows are cast across the surface, especially during different seasons on Mars. Solar flares and coronal mass ejections contribute to changes in atmospheric pressure, which can alter the distribution of dust and aerosols. These particles play a crucial role in scattering sunlight, thus affecting the length and darkness of shadows. Observing these phenomena over time allows researchers to correlate solar events with alterations in shadow characteristics across various Martian terrains. Data collected from orbiters and rovers provides a wealth of information. High-resolution imaging reveals how shadows stretch and shift, creating a visual record of solar cycles. This evidence supports the hypothesis that solar activity can significantly impact shadow dynamics. Continuous monitoring of solar phenomena enables scientists to refine their understanding of these interactions, leading to more precise models. This ongoing research not only illuminates the behavior of shadows on Mars, but also enhances knowledge of how solar activity influences planetary environments throughout the solar system. Analyzing these relationships deepens comprehension of Mars's climatic evolution and atmospheric behavior. Seasonal changes on Mars induce significant variations in shadow length and orientation, directly linked to the planet's axial tilt and elliptical orbit. During its summer solstice, the proximity to the Sun increases solar insolation, affecting temperature and atmospheric density. Shadows cast by Martian topography fluctuate in length, with longer shadows emerging in the cooler seasons due to lower solar elevation angles. Regions near the equator experience pronounced differences, where shadows can stretch dramatically during the winter months. This phenomenon creates stark contrasts across the landscape, highlighting geological features that might otherwise remain obscured. In polar regions, shadows take on unique shapes as the sun dips below the horizon, resulting in extended periods of twilight. Orientation shifts also illustrate the planet's dynamic environment. As Mars progresses through its seasons, the alignment of shadows changes, revealing geologic formations and subsurface structures. These directional variations provide crucial insights into the surface composition and geological history. The interplay between solar position and surface topography allows scientists to model and predict the effects of these seasonal changes on Martian weather patterns. Understanding how shadows transform can elucidate the processes that govern atmospheric phenomena, contributing to the broader knowledge of Martian climatology and aiding in future explorations of this enigmatic planet. The influence of Martian winds on shadow patterns reveals intricate interactions between atmospheric dynamics and surface features. These winds, often swift and unpredictable, sculpt the landscape, creating transient formations that alter how light behaves upon contact with the terrain. Dust storms, common in this region, contribute to the shifting visual landscape, casting ephemeral shadows that change with every gust. Surface topography plays a critical role in this process. The elevation of rocks or the depth of craters can cause shadows to stretch or contract, depending on the angle of incoming sunlight. This variability directly affects how shadows are perceived from orbit, enabling scientists to map wind patterns and their intensity. In addition, the interplay between dust and wind creates atmospheric conditions that can obscure shadows altogether. Fine particles suspended in the atmosphere scatter sunlight, diminishing contrast and leading to a more uniform illumination across vast expanses. Observations from orbiters provide invaluable data, allowing researchers to quantify these effects and establish correlations between wind speed, dust concentration, and shadow behavior. Understanding these relationships not only enhances knowledge of Martian winds, but also aids in deciphering the planet's broader climatic patterns. The implications for future missions are profound, as accurate predictions of atmospheric conditions will facilitate safer landings and more effective exploration techniques. Gale Crater serves as a key site for understanding the intricate relationship between impact features and atmospheric phenomena. This region, with its towering central peak and layered sedimentary deposits, provides a unique window into the planet's geological history. The shadow cast by its imposing walls creates microclimates, influencing temperature and wind patterns. Observations reveal variations in dust movement linked to these shadowed areas, where fine particles accumulate and persist, shaping the local environment. Research indicates that the interplay of sunlight and shadow contributes to temperature differentials that can impact the behavior of Martian dust storms. The crater's topography affects solar heating, creating zones where the air is cooler and denser, affecting wind currents. These currents can either disperse dust or cause it to settle, revealing the dual nature of these shadows. The layering of materials within the crater also presents a historical record, capturing the effects of past environmental conditions. Granular analysis of the sediments shed light on water activity and potential habitability in earlier epochs. The study of these impact features not only enhances the understanding of Mars' climatic history, but also informs strategies for future exploration. The relationship between geological structures and atmospheric dynamics continues to unveil the complexities of this enigmatic world. Each observation adds depth to the ongoing quest to comprehend Martian evolution. The phenomenon of shadow casting presents a unique opportunity to study Martian eclipses. These events occur when one celestial body obstructs the light from another, resulting in temporary obscuration. On Mars, this typically involves its two moons, Phobos and Deimos, which are irregularly shaped and display distinct characteristics. Their rapid orbits contribute to the brief duration of eclipses, often lasting only a few minutes. Observations reveal that the shadows cast by these moons exhibit peculiar patterns on the Martian surface. They can stretch for several kilometers, creating darkened patches that provide insights into the moon's trajectories and physical dimensions. Detailed analysis of these shadow patterns allows researchers to refine models concerning the gravitational influence exerted by Phobos and Deimos. Each eclipse serves as a natural laboratory, facilitating measurements of light variations that can enhance understanding of the Martian atmosphere. Changes in brightness during these events indicate atmospheric composition and density, contributing vital data to ongoing atmospheric studies. This region of inquiry reflects not only the dynamics of Martian celestial mechanics, but also the intricate interplay between light and shadow. The shadows themselves, fleeting yet impactful, reveal the complex relationship between Mars and its satellites, offering a glimpse into the evolutionary history of the red planet. Although all these nouns of solar position significantly affects shadow dynamics on Mars, shaping the contours and lengths of these ephemeral shapes. Variations in sunlight intensity, stemming from the planet's axial tilt and orbital eccentricity, result in differing illumination angles across its surface. In this region, shadows lengthen dramatically during the Martian winter, extending toward the horizon as the sun dips low in the sky. Conversely, during summer, the sun's high trajectory minimizes shadow lengths, creating stark contrasts against the arid landscape. Solar storms, prevalent in this atmosphere, also introduce fluctuations in light intensity. These disturbances can temporarily obscure the sun, modifying shadows and their visibility. The interplay of solar radiation and Martian features, such as craters and valleys, creates a unique interplay of light and dark, revealing geological details that might otherwise remain hidden. Observations from orbiting satellites contribute crucial data, further detailing how these phenomena interact with the Martian surface. They capture the shadows cast by both natural formations and human-made structures from past exploration efforts. These records not only enhance understanding of shadow behavior, but also provide insight into the environmental conditions that have shaped Mars over eons. The intricate dance of light and shadow offers a subtle yet compelling narrative, chronicling the ongoing evolution of this enigmatic planet. The geophysical properties of Mars exert significant influence on the formation and behavior of shadows across its surface. The thin atmosphere, composed predominantly of carbon dioxide, allows sunlight to penetrate with minimal scattering. This results in sharp contrasts between illuminated areas and the encroaching darkness of shadows. The Martian terrain, characterized by vast plains, imposing volcanoes, and deep canyons, contributes to the varying lengths and angles of shadows cast by structures such as rocks and landforms. Surface features dictate how light interacts with the ground. Dust-covered regions exhibit increased albedo, reflecting sunlight and altering the apparent intensity of shadows. In contrast, darker basaltic rock provides a stark background, intensifying the depth of shadows. This interplay is particularly pronounced during the Martian solstice, when solar angles shift dramatically, causing elongated shadows that stretch across the landscape. Temperature variations also play a role. The cold Martian nights bring a sharp drop in temperature, causing shadows to maintain their form longer than they would under warmer conditions. These persistent shadows can obscure details in the terrain, creating areas of phantom-like mystery, where scientific exploration reveals surprising geological features. Understanding these dynamics enhances comprehension of Martian geology and aids in the search for signs of past water flow, further unraveling the planet's complex history. Ho-Hull Street Bar Maestra Trigonal data provides a critical foundation for understanding current shadow phenomena on Mars. Records of previous missions, including imagery and spectral analysis, reveal how shadows have shifted over decades, influenced by atmospheric conditions and seasonal cycles. This extensive archive enables scientists to compare present observations with those captured in earlier missions, facilitating a deeper exploration of the Martian surface and its evolving features. Longitudinal studies indicate that variations in shadow length and intensity correlate with topographical changes, particularly in areas where erosion and sediment deposition have occurred. These changes, documented over time, offer insights into the geological processes shaping the planet. Shadows cast by Martian terrain reveal the underlying topography, unveiling hidden structures and formations that remain obscured in direct sunlight. Analysis of shadows in conjunction with historical data also aids in calibrating current instruments, improving the accuracy of measurements related to surface temperature, albedo, and atmospheric density. Such calibration ensures that scientists can draw reliable conclusions from contemporary data, reinforcing or challenging previous hypotheses regarding Martian climate and geological activity. This ongoing synthesis of historical and current observations contributes significantly to the understanding of how shadow phenomena interact with the environment. This understanding opens up pathways to explore the Martian landscape's ancient rivers and lakes. Evidence suggests that these features once thrived, shaping the planet's surface through erosion and sediment deposition. Shadows cast by the rugged terrain reveal subtle variations in elevation and composition, which hint at the locations of former water bodies. Detailed analysis of these shadows, combined with high-resolution imagery, uncovers patterns indicative of ancient waterways. This region exhibits the remnants of meandering channels, paralleling features seen in terrestrial river systems. The interplay of shadow and light uncovers not only the contours of these channels, but also their geological context, suggesting a once active hydrological cycle. Ancient lakes, now dry and desolate, offer insights into past climates. The shadowing effect helps identify basin outlines, where sedimentary deposits hint at fluctuating water levels over millennia. These findings imply that the planet experienced significant climatic shifts, transitioning from a wet to an arid environment. Such insights into Martian hydrology reshape current understanding of its potential to support life by reconstructing the history of these ancient rivers and lakes through shadow analysis. Scientists gain a clearer picture of the conditions that may have existed, lending credence to theories about life's possibility on the surface of Mars. The mystery of Martian shadows continues to illuminate paths to the past. Investigating surface materials reveals an intricate relationship with shadows. Various minerals, dust, and rock types interact uniquely with light and darkness, shaping the landscape's appearance. The fine regolith, composed of tiny particles, reflects light differently than the more coarse, rocky terrains. This variation in texture alters shadow length and intensity, creating a striking contrast that aids in geological understanding. Observations from orbiting satellites have provided detailed maps of these materials, enhancing comprehension of how shadows define and delineate regions. Darker surfaces absorb more sunlight, resulting in deeper shadows, while lighter materials reflect light, casting shallower silhouettes. This dichotomy assists researchers in identifying mineral compositions, revealing the geological history embedded in the Martian crust. The presence of iron-rich minerals, for example, is often highlighted in shadowed areas where they maintain cooler temperatures compared to surrounding surfaces. This thermal inertia can affect atmospheric conditions, contributing to localized weather patterns. Shadows thereby serve as indicators, guiding scientists toward potential resources and past environmental conditions. Studies of these interactions also unveil changes over time, as seasonal variations influence the movement of dust and the shifting of materials. The constant interplay between light and shadow becomes a silent chronicle, reflecting the planet's dynamic history and ongoing evolution, a testament to the forces shaping this enigmatic world. These observations hold significant implications for future Mars exploration, as understanding the patterns of shadow can illuminate geological processes and potential resource locations. Variations in shadow lengths and angles provide crucial data on the planet's topography and surface composition. Such insights may lead to the identification of mineral deposits or subsurface water reserves, both vital for sustaining human presence. On the quest to uncover the mysteries of this region, these shadows serve as natural indicators of the Martian day-night cycle and seasonal changes. The cyclical nature of these phenomena may offer guidance on the timing of exploration missions, optimizing conditions for both robotic and human activities. Detailed studies have revealed that shadows can also affect temperature variations across the Martian surface. Recognizing these thermal gradients can aid in selecting landing sites for future missions, ensuring equipment remains operational in the planet's harsh climate. The silent narratives embedded in the shadows can enhance our understanding of Martian weather patterns. By analyzing how shadows shift over time, scientists may glean insights into atmospheric changes and their impact on surface conditions. Such knowledge expands our ability to predict Martian weather and adapt exploration strategies accordingly. The contributions of citizen science have increasingly become integral to shadow research on Mars. This collaborative effort invites enthusiasts and amateur scientists to participate in data collection and analysis, providing a fresh perspective on the complexities of the Martian environment. Volunteers engage in scrutinizing images captured by orbiters, identifying subtle changes in shadow patterns that reveal information about surface features and atmospheric phenomena. Volunteers Malpuralime platforms, citizen scientists can easily share their findings, contributing to a larger database accessible to researchers around the globe. This collective endeavor enhances the understanding of seasonal shadow variations influenced by the planet's axial tilt and orbital eccentricity. These observations are crucial for assessing the potential for past or present life, as shadows often indicate areas of interest for further exploration. In addition, the engagement of the public fosters a sense of shared ownership in scientific discovery. It bridges the gap between professional researchers and the general populace, creating a community that thrives on curiosity and collaboration. The integration of citizen data into formal research enables scientists to validate findings and develop refined models of Martian conditions. This collaborative spirit not only enriches the scientific process, but also exemplifies the power of collective inquiry, paving the way for future explorations and discoveries on the Red Planet. The theory of shadow casting in Martian regolith presents a complex interplay of light and surface texture. Variations in the mineral composition and granularity of the regolith lead to distinct shadow patterns, which can be analyzed to infer information about the terrain. Observations show that finer particles tend to diffuse light differently than coarser grains, resulting in unique shadow formations that can reveal underlying geological processes. This phenomenon enables researchers to assess the topography and composition of the Martian surface. Shadows cast by rocks and boulders contribute to the understanding of their size and shape, while the interaction between sunlight and regolith grains helps in identifying the material properties of the soil. Such insights are vital for future missions, as they inform landing site selection and resource utilization strategies. The interplay of light and surface morphology also aids in detecting seasonal changes across the Martian landscape. Variations in shadow length and intensity can signal shifts in temperature or atmospheric conditions, providing valuable data for climate studies. The examination of these shadows offers a window into the planet's past and present, shedding light on its geological history and potential for supporting life. Space missions have played an instrumental role in unraveling the mystery of Martian shadows. This region, characterized by its varied topography and atmospheric nuances, has been the focus of numerous robotic explorers. Each mission has contributed invaluable data, enhancing the understanding of shadow dynamics across the surface. High-resolution imaging from orbiters reveals the intricate details of shadow formations, which are influenced by the planet's topography and seasonal changes. Rovers, equipped with advanced scientific instruments, have ventured into these shadowed areas, collecting samples and conducting in situ analysis. Their findings have uncovered the mineral composition of the surface, providing context for the shadows observed from orbit. The interplay between sunlight and the Martian terrain generates shadows that serve as indicators of geological features such as craters, valleys, and potential subsurface ice deposits. Data from various instruments, including spectrometers and cameras, allow researchers to analyze shadows in conjunction with atmospheric conditions. These observations reveal how dust storms and seasonal variations impact visibility and shadow length. Understanding the temporal changes in these shadows is crucial, as it may correlate with climatic shifts and their effects on Martian geology. Collectively, these missions contribute to a growing body of knowledge, revealing the complexity of shadows on Mars and their implications for the planet's environmental history. Each discovery adds another layer to the narrative of this enigmatic world. Multispectral imaging plays a crucial role in unraveling the complexities associated with Martian shadows. This technique allows scientists to capture data across various wavelengths, providing a richer view of surface materials and their properties. It reveals subtle variations undetectable by traditional imaging methods, uncovering hidden details that inform theories regarding the planet's geological history. In shadow analysis, this method is particularly beneficial. Shadows can obscure features, yet multispectral data can penetrate these dark areas, allowing for the identification of mineral compositions and surface textures. This capability aids in distinguishing between volcanic rock, sedimentary deposits, and the presence of ice or water, all of which are vital clues to understanding the planet's past. The integration of multispectral imaging with robotic missions has enhanced the accuracy of observations. Rovers equipped with this technology capture images that enable researchers to analyze how solar radiation interacts with different materials. The resulting data sheds light on seasonal changes, including variations in temperature and atmospheric conditions, which influence shadow formation. Such insights contribute to a broader understanding of Martian climate dynamics and geological processes. They assist in predicting how shadows may evolve over time, influencing future exploration strategies. This meticulous examination of shadows serves as a gateway to comprehending Mars, revealing the complexities of a world that has long captivated human curiosity. Investigating shadow variability across various Martian regions uncovers a spectrum of phenomena that enhance understanding of the planet's intricate surface. The northern plains exhibit shadows that shift dramatically due to seasonal changes, influenced by the tilt of the planet's axis. Here, the play of light and dark transforms the landscape each sol, hinting at unseen geological processes beneath the surface. In contrast, the towering Tharsis volcanoes present a different case. Shadows cast by these colossal formations reveal the interplay of elevation and atmospheric conditions. As sunlight filters through the thin Martian atmosphere, the shadows lengthen, providing insights into the height and structure of these ancient giants. The analysis of these variations aids in deciphering the planet's geological history. Cratered regions, such as Hellas Planitia, offer another layer of complexity. Shadows within these basins can indicate differences in surface composition and the presence of frost, shaped by subtle shifts in temperature and atmospheric pressure. Observations from orbiting satellites have recorded the nuances of these shadows, contributing to a broader understanding of Martian weather patterns. Each case study exemplifies the rich variability of shadows on Mars, emphasizing their role as indicators of environmental change. This ongoing research continues to enhance the knowledge of a planet that remains an enigma, inviting further exploration and discovery. International collaboration plays a crucial role in advancing Martian shadow research. Various space agencies and institutions around the world contribute their expertise and resources, creating a synergistic effect that propels scientific understanding. This pooling of knowledge allows for a diverse range of methodologies and technologies to be applied, resulting in more comprehensive studies of shadow phenomena on Mars. Hivels dius bevondholdency and the atation third. Observations from orbiters, landers, and rovers are exchanged among researchers, facilitating a broader analysis of the Martian surface and its atmospheric conditions. The integration of findings from different missions enables scientists to create more accurate models of shadow behavior and its implications for climate and geological processes. Collaborative missions also foster innovation Joint projects can lead to the development of advanced instrumentation specifically designed to study Martian shadows. These tools can measure light scattering, surface reflectivity, and atmospheric composition, providing critical insights into the planet's unique characteristics. Furthermore, international partnerships promote inclusivity in the scientific community. Researchers from various countries contribute their unique perspectives, enriching the understanding of Martian phenomena. This collective effort not only enhances the quality of research, but also strengthens the global pursuit of knowledge about the cosmos, ensuring that the mysteries of Mars are approached with a united front. The prospects for Martian shadow studies lie in the integration of advanced technologies and collaborative frameworks. Upcoming missions are poised to deploy an array of sophisticated instruments designed to capture unprecedented data about shadow phenomena on the Martian surface. These instruments will enable scientists to measure light variations, temperature fluctuations, and atmospheric conditions with enhanced precision, revealing how shadows interact with environmental factors. Challenges persist, particularly in the harsh Martian environment. Dust storms and radiation levels complicate data collection and require robust engineering solutions. The development of resilient materials for instruments is crucial, ensuring functionality despite extreme temperatures and abrasive conditions. In addition, analyzing the gathered data will demand innovative algorithms and techniques capable of processing vast amounts of information. Machine learning and artificial intelligence may play pivotal roles in identifying patterns that are not immediately apparent to human researchers. International collaboration remains essential, as diverse expertise can lead to breakthroughs previously unattainable by individual entities. The synthesis of findings from various teams can provide a more comprehensive understanding of Martian shadows and their implications for surface processes and potential habitability. The journey ahead encompasses both promise and obstacles, but with concerted efforts, the enigmatic shadows of Mars may finally unveil their secrets, shedding light on the planet's past and guiding future exploration. Intriguingly, the connection between Martian shadow patterns and crater dating emerges as a pivotal aspect of understanding the planet's geological history. Craters, formed by impacts over eons, serve as time markers within the Martian landscape. The interplay of shadows cast by these craters during different solar positions can reveal nuances about their age and formation processes. In this region, shadows lengthen or shorten depending on the sun's elevation, highlighting features that may otherwise remain obscured. By analyzing these patterns, researchers can infer the relative ages of craters, as older craters exhibit more pronounced shadowing due to erosion and sediment deposition. This methodology allows for precise dating, providing insights into the chronological sequence of Martian surface evolution. Recent studies employ high-resolution imaging and computational modeling to decode the shadows. Advanced algorithms quantify their dimensions, correlating them with crater morphology. This correlation aids in reconstructing the Martian timeline, illustrating intervals of geological activity and inactivity. Understanding these shadows leads to further implications regarding the planet's climate history and potential for past life. Each shadow carries with it a silent testimony of the forces that have shaped this alien world. In unraveling the complexities of shadow patterns, the intricate narrative of Mars awaits discovery, bridging the past with future explorations of its surface and subsurface mysteries. The surface interactions of light and shadow on Mars reveal critical insights into its environmental conditions. These patterns influence temperature fluctuations, soil compositions, and even the potential for microbial life to thrive. Shadows provide shelter from ultraviolet radiations, which is intense on the Martian surface. The regions they create may harbor moisture and maintain temperatures conducive to life, albeit in a dormant state. Variations in shadow length and position across the seasons inform scientists about the changing dynamics of the Martian atmosphere. They indicate where heat is retained or lost, which is essential for understanding how water, in any form, might persist. Such insights are vital for astrobiological studies, suggesting areas that could support life or have done so in the planet's past. The interplay of light and shadow also affects the visibility of minerals and geological structures, guiding exploration missions to sites where life may once have flourished. The discovery of organics in shadowed regions could bolster theories regarding life's resilience in extreme environments. In deeper investigations, understanding how shadows interact with Martian soil may lead to revelations about subsurface water reservoirs, offering clues about the planet's climatic history and its potential to support life. Each shadow becomes a marker of where the search for life may focus in future missions. The role of shadow extends beyond mere markers. It provides critical insights into Martian weather patterns. Observations of these shadows during the changing seasons reveal variations in temperature and atmospheric pressure. When sunlight is obstructed, localized cooling occurs, influencing wind currents and the distribution of dust. This cooling effect creates a ripple in the atmosphere, allowing scientists to discern the complex interactions within Martian climatology. Dust storms, prevalent in this region, are significantly influenced by the interplay of light and shadow. Where shadows linger, the ground remains cooler, affecting the thermal gradient that fuels wind formations. By analyzing the shadows cast during these storms, it is possible to discern their movement and intensity. This information is crucial for predicting weather events that may impact future exploration missions. Additionally, the seasonal migration of shadows offers vital clues about surface features. Changes in shadow length and orientation can indicate shifts in terrain, such as the movement of sand dunes or the melting of frost. Each observation adds a layer of understanding to the Martian environment, allowing researchers to develop more accurate models of its climate. In turn, these models inform strategies for sustainable human presence on the planet, ensuring that exploration efforts are guided by the intricate dance of light and shadow across the Martian surface. The interplay between geology and shadow anomalies reveals vital insights into Martian topography. These shadows, formed by the sun's angles striking varied landscapes, expose the intricacies of the planet's surface features. Distinct geological structures, from towering volcanoes to expansive canyons, create unique shadow patterns that hint at their composition and age. In particular, the layered deposits found in the Valle Marinaris region exhibit pronounced shadowing effects, illustrating the stratified history of sedimentation and erosion. Shadows cast by these formations help researchers identify past climatic conditions, revealing a timeline of volcanic activity and potential water presence. The nuances in shadow lengths and shapes indicate variations in slope and texture, essential for deciphering the geological processes that have shaped this environment. These shadow anomalies also assist in identifying potential resources. Areas where shadows linger longer may indicate mineral-rich deposits, guiding future exploration priorities. Understanding the relationship between geology and shadows enhances the ability to predict how these landscapes might change under different solar conditions. Furthermore, this knowledge aids in anticipating the challenges future missions may encounter. The interaction between light and Martian geology not only deepens the comprehension of its past, but also lays a foundation for sustainable human exploration, highlighting the significance of shadows in shaping both the present and future narratives of Mars. Shadows play a crucial role in the planning of future Mars missions. These elongated silhouettes inform scientists about terrain features that are otherwise obscured under the harsh glare of sunlight. The varying lengths and angles of shadows can reveal the height of geological structures, such as cliffs and craters, providing essential data for landing site selection. This region's shadow patterns also assist in identifying potential hazards, guiding the safe navigation of rovers and crewed missions. In addition, shadows serve as indicators of seasonal changes on the Martian surface. The interplay between sunlight and the Martian atmospheric conditions influences the formation and melting of frost, which may be essential for understanding water availability. The seasonal dynamics captured through shadow analysis could be pivotal in determining optimal times for exploration and resource extraction. These studies extend beyond mere observation. They inform technological development. Solar panels designed for rovers and habitats must adapt to the shifting shadows cast by surrounding topography, maximizing energy efficiency. Understanding the impact of shadows can lead to innovations in design and operation, ensuring that resources are utilized effectively. Mathematical models play a pivotal role in predicting shadow behavior on Mars. These models provide a framework for understanding how shadows interact with the uneven terrain and atmospheric conditions of the planet. Variables such as solar angle, surface topography, and atmospheric density are meticulously analyzed to generate accurate predictions. Such models rely on complex algorithms that simulate the interplay of light and shadow, facilitating a deeper comprehension of their dynamics. In this context, the mathematical representation of shadows becomes essential for various applications, from rover navigation to the optimization of energy collection through solar panels. By quantifying the effects of shadows on different surfaces, it is possible to devise strategies that mitigate their impact on solar efficiency. When shadows fall over solar arrays, they can significantly reduce energy output, making precise predictions critical for mission success. Incorporating data from Mars rovers and orbiters enhances the accuracy of these models. Measurements taken from the Martian surface allow for real-time adjustments to be made, improving the reliability of predictions. This synergy between observational data and mathematical modeling enables researchers to refine their understanding of shadow behavior. Analyzing the effects of Martian temporality on shadows reveals intricate patterns shaped by the planet's unique rotational and orbital characteristics. The day length on Mars, lasting approximately 24 hours and 37 minutes, introduces subtle variations in shadow length and orientation. These differences become pronounced at different latitudes, where the angle of sunlight shifts dramatically with the seasons. The axial tilt of about 25 degrees contributes to pronounced seasonal changes. During the summer solstice in either hemisphere, shadows contract significantly due to the sun's elevated position. Conversely, during the winter solstice, shadows elongate, stretching across the barren landscape, evoking a quiet reminder of the planet's harsh climate. Atmospheric conditions also play a critical role. The thin Martian atmosphere, composed primarily of carbon dioxide, allows for minimal scattering of light, resulting in sharp, defined shadows. Dust storms can temporarily obscure this clarity, altering the visual landscape and creating an ephemeral obscurity that challenges the precision of observational studies. The interplay of these factors results in a dynamic interplay between sunlight and shadow, providing insight into the Martian environment. Variations in shadow behavior not only assist in understanding surface topography, but also contribute to broader implications regarding potential exploration and habitability on this enigmatic planet. The analysis of shadow dynamics on Martian dunes reveals intricate patterns that informs scientists about the planet's geological history. These dune formations, shaped by wind erosion and sediment transport, exhibit distinct variations in shadow length and orientation throughout the Martian sol, or day. This phenomenon is largely influenced by the planet's axial tilt and the position of the Sun in its thin atmosphere. Shadows cast by the dunes indicate changes in surface texture and composition, providing clues about the processes responsible for their formation. The contrast between light and shadow across the dunes highlights the subtle nuances of the Martian landscape. Different materials reflect sunlight variably, resulting in shadow play that can elucidate the physical properties of these features. These observations are crucial for understanding how wind patterns have sculpted the landscape over millions of years. The dynamics of the shadows reveal not only the current state of the dunes but also their evolutionary history, suggesting cycles of activity and dormancy. Detailed studies utilizing high-resolution imaging and advanced modeling techniques can enhance this understanding. By comprehensively mapping these shadow behaviors, researchers can develop predictive models that may assist future exploration missions. Insights gained from the shadow dynamics of Martian dunes contribute significantly to the ongoing quest to unravel the mysteries of this otherworldly environment. Enhancing our knowledge of planetary geology, the scientific community plays a pivotal role in advancing the understanding of Martian phenomena. Collaborative efforts among researchers facilitate the sharing of diverse expertise, enabling a more comprehensive approach to complex challenges. This synergy encourages innovative methodologies, yielding insights that surpass the capabilities of isolated studies. Interdisciplinary teams, comprising planetary scientists, geologists, and atmospheric physicists, exemplify the strength of collaboration. Each discipline brings a unique perspective, allowing for a multifaceted examination of Martian features. By integrating remote sensing data with ground-based observations, these specialists can create intricate models that simulate shadow behavior on the planet's surface. International partnerships also enhance the research landscape. Space agencies and institutions worldwide contribute a wealth of resources and knowledge, fostering an environment of shared discovery. Such alliances not only expand the scope of investigations, but also promote a unified mission in exploring Mars. As findings emerge, collaborative platforms facilitate the dissemination of research outcomes. Open access publications and conferences encourage dialogue among scientists, ensuring that insights gained are accessible to the broader community. This interconnectedness cultivates an atmosphere of continuous learning where each discovery informs subsequent research. The importance of educational outreach in shadow studies cannot be overstated. Engagement initiatives foster a deeper understanding of the complexities surrounding Martian shadows and their implications for planetary science. Classroom programs introduce students to the fundamental principles of light and shadow, utilizing simulations that replicate Martian conditions. This hands-on approach encourages critical thinking and sparks curiosity about the natural world beyond Earth. Workshops and public lectures extend this knowledge to broader audiences, bridging the gap between researchers and communities. These events often feature interactive demonstrations, allowing participants to visualize the mechanics of light behavior on Mars. Such experiences demystify scientific concepts and promote a culture of inquiry, where questions regarding planetary environments are encouraged. Collaborations between universities and space agencies amplify the impact of outreach efforts. Graduate students often lead educational campaigns, sharing their research findings and personal experiences in the field. This mentorship fosters a new generation of scientists, equipped with both knowledge and passion for exploration. In remote regions, mobile learning units travel to schools, ensuring that even those in underserved areas have access to cutting-edge science. By integrating shadow studies into educational curricula, a foundation is laid for future research endeavors. Bridging the gap between Mars shadow research and Earth science reveals the interconnectedness of planetary studies. Insights gained from the shadows cast by Martian topography can illuminate terrestrial phenomena. Shadows on Mars, influenced by its unique geological features, serve as analogues for understanding similar processes on Earth. This relationship fosters a comparative analysis, enhancing the understanding of both planetary atmospheres. Investigating the angles and lengths of shadows on Mars provides critical data about its surface conditions and atmospheric composition. These measurements assist in refining models of light interaction with various materials, applicable to Earth's own materials. Shadows shaped by Martian dust storms, for instance, mirror the effects of atmospheric disturbances on Earth. Observing these processes can yield valuable information regarding climate dynamics. The technology developed for shadow analysis on Mars, including precision imaging and computational modeling, finds utility in Earth-based applications. Such tools enhance the accuracy of weather forecasting and disaster management strategies. Collaborative efforts between Mars researchers and Earth scientists are essential for advancing knowledge in planetary science as a whole. These initiatives cultivate a richer understanding of planetary systems, promoting the realization that phenomena occurring in the vast expanse of space may reflect similar patterns closer to home. Such connections reveal an intricate relationship between time zones and the perception of shadows on Mars. The planet's rotation period, lasting approximately 24 hours and 39 minutes, introduces unique challenges for understanding light and shadow dynamics. This slight variation creates a subtle yet notable difference in shadow length and orientation, depending on the observer's location on the Martian surface. The resemblance of the two Martian hemispheres cannot be overstated. Each region experiences seasonal shifts due to its axial tilt of about 25 degrees, which alters the sun's position in the sky. In the northern hemisphere, summer months yield longer days and shallower angles of sunlight, producing elongated shadows that stretch across the rugged terrain. Conversely, winter months cast short, sharp shadows, enhancing the contrast of the surface features. Observations from various missions have captured these phenomena, revealing that local topography plays a pivotal role in shadow behavior. Craters, cliffs, and valleys create complex interactions of light that can mislead perception. These variations underscore the importance of careful calibration in imaging systems to ensure accurate representation of Martian shadows. Understanding how time zones affect shadow perception provides vital insights into the planet's atmospheric conditions, surface composition, and geological history, facilitating a deeper comprehension of this enigmatic world. Shadow analysis in Martian crater exploration reveals critical information regarding the surrounding terrain and geological features. Shadows cast by the unique topography offer clues about the time of day and seasonal changes on the planet. The length and orientation of these shadows can indicate the height of surrounding cliffs and the depth of craters. This information assists scientists in creating three-dimensional models of these landscapes, enhancing understanding of the underlying geology. In particular, the interplay of light and shadow allows researchers to identify potential deposits of ice or other volatiles hidden beneath the surface. These resources are essential for future exploration and potential colonization efforts. It also highlights the role of shadows in detecting changes over time. Subtle shifts in shadow patterns can signal erosion or sediment deposition, providing insights into active processes shaping the Martian surface. The use of high-resolution imaging from orbiters and rovers aids in this analysis, revealing details not visible to the naked eye. Shadows serve as natural markers, guiding scientists to areas of interest where further study may yield significant discoveries.
The consistent observation of these phenomena contributes to a broader understanding of Mars's climate history and its capacity to support life. Such meticulous examination of shadows forms a vital component in unraveling the mysteries of this intriguing planet. Longitudinal studies provide essential insights into the patterns and behaviors of shadows across the Martian landscape. By observing the same regions over extended periods, researchers can identify subtle changes that may indicate shifts in atmospheric conditions or surface characteristics. These observations are invaluable for understanding how shadow lengths and angles vary with the seasons on Mars, which are markedly different from those on Earth due to its axial tilt and elliptical orbit. In this context, it becomes clear that specific geological features, such as craters and cliffs, cast varying shadows at different times of the Martian year. The interplay between light and surface texture can reveal information about the composition and erosion processes affecting these formations. Detailed analysis of shadow dynamics allows scientists to infer the relative heights of Martian terrain and the potential existence of previously uncharted topographies. Over time, the accumulation of shadow data can yield a comprehensive understanding of Martian weather patterns. Fluctuations in shadow behavior may correlate with dust storms, temperature changes, and even the presence of water ice deposits. This relationship helps to construct a more nuanced view of the Martian environment, where shadows are not mere absence of light, but rather indicators of the planet's evolving landscape and climatic intricacies, reflecting its history and informing future exploration efforts. The evolution of shadow research on Mars has transitioned from rudimentary observations to advanced analytical techniques that reveal intricate details of the planet's surface. Early studies relied heavily on visual interpretation, with scientists cataloging shadow formations through simple photographs taken by orbiters. Over time, this approach expanded into the utilization of more sophisticated imaging technologies, enabling the capture of high-resolution data. Advancements in remote sensing tools have allowed researchers to analyze shadow characteristics with unprecedented precision. Light detection and ranging, alongside multispectral imaging, contribute significantly to understanding how shadows interact with Martian terrain. These techniques facilitate the exploration of topographical variations, revealing subtle changes in elevation and surface composition that might otherwise remain hidden. Recent developments in computational modeling further enhance the capacity to interpret shadow data. Algorithms simulate how light interacts with the Martian surface, predicting shadow lengths and shapes based on varying solar angles. Such simulations enable scientists to visualize seasonal changes, offering insights into the planet's climatic patterns. The culmination of these efforts leads to a comprehensive understanding of how shadows serve as indicators of geological and atmospheric processes. They provide clues about water activity, potential ice deposits, and surface erosion, guiding future missions and informing the ongoing quest to uncover the secrets of Mars. Predictive models are now being developed to analyze the patterns of shadows across the Martian landscape. These advancements leverage data from numerous orbiters and rovers, integrating various observational perspectives to form a cohesive understanding of the planet's topography. This region, shaped by eons of geological activity, presents opportunities for identifying previously unseen features. The interplay of sunlight and topographical variations creates an intricate web of shadows, revealing intricate details about the surface composition. This process allows scientists to make informed predictions about where significant discoveries might lie. Seasonal changes on Mars additionally influence shadow lengths and angles, providing a temporal dimension to the study. Observations from orbital missions enhance this understanding, capturing the dynamic nature of shadow patterns across Martian seasons. Technological innovations, such as advanced imaging techniques, further refine the ability to detect subtle changes in shadow characteristics. By mapping these variations over time, researchers can track shifts in surface materials and potential changes in climate. The integration of artificial intelligence into data analysis presents new possibilities for discerning patterns that were once too complex for manual interpretation. Increased collaboration between planetary scientists and engineers will facilitate the design of future missions aimed at directly exploring shadow-rich regions where the potential for groundbreaking discoveries remains high. Each new insight contributes to the broader understanding of Mars and its enigmatic past. Phosphoration of Martian shadows offers profound implications for planetary sciences. These observations reveal the intricate relationship between surface features and atmospheric dynamics. Shadows, cast by towering volcanoes or deep canyons, serve as natural markers, allowing scientists to infer the heights and depths of various geological structures. The shadows shift as the sun traverses the Martian sky, providing a dynamic perspective that enhances three-dimensional mapping of the terrain. Analysis of these shadows also aids in understanding the planet's climate history. Variations in shadow lengths correlate with seasonal changes, highlighting the oscillations of temperature and atmospheric pressure. Studying these fluctuations reveals patterns that hint at the planet's ancient climatic conditions, possibly even the presence of liquid water in its past. The impact extends beyond Mars itself. Insights gained from shadow studies contribute to comparative planetology by drawing parallels between Martian shadows and those on other celestial bodies. Scientists can refine their models of planetary atmospheres and surfaces throughout the solar system. This knowledge enhances theories related to planetary formation and evolution. As research progresses, the implications of these Martian shadows continue to resonate, reinforcing the interconnectedness of planetary systems. Each discovery builds upon the last, revealing layers of complexity within our cosmic neighborhood. Data integrity serves as the backbone of shadow research, ensuring that findings are reliable and conclusions drawn from them are valid. In the realm of Martian studies, maintaining accuracy becomes paramount due to the planet's distance and the intricacies involved in its atmospheric behavior. Observations must be meticulously calibrated to account for variables such as dust storms, solar cycles, and seasonal changes. These factors can significantly distort measurements and lead to misinterpretations. The utilization of advanced technologies, including high-resolution imaging and sophisticated spectrometry, enhances the quality of data collected. Instruments must withstand the harsh conditions of the Martian environment while delivering precise readings. Each data point contributes to a larger mosaic, informing scientists about shadow patterns and their implications for understanding Martian geology. Collaboration among research teams further reinforces data integrity. Sharing findings and methodologies allows for cross-validation of results, reducing the risk of error. Peer-reviewed publications serve as a checkpoint, ensuring that only well-substantiated claims enter the scientific discourse. This comprehensive approach to data integrity not only bolsters the credibility of Martian shadow research, but also fosters an environment of growth and discovery. As researchers refine their techniques and deepen their understanding, the shadows of Mars unveil more of their secrets, illuminating the planet's past and potential for future exploration. The implications of uncovering the Martian shadow mystery extend far beyond the planet itself. Insights gained from these investigations contribute to our broader understanding of planetary atmospheres and geological processes. Each shadow reveals the interplay of light and terrain, offering clues about the Martian surface's composition and history. This knowledge aids in constructing a more detailed picture of how celestial bodies evolve over time under varying conditions. Furthermore,
Advancements in shadow analysis inform future missions. The data collected not only enhances navigational methods, but also provides vital information for selecting landing sites that are scientifically rich areas of interest, once obscured by shadows, can now be prioritized for study, enabling targeted exploration that maximizes scientific return. The ongoing study of these phenomena fosters a sense of interconnectedness within the scientific community. Collaboration across disciplines accelerates progress, as experts in atmospheric science, geology, and astronomy converge to interpret findings. This unified approach encourages innovation, paving the way for new technologies that may one day allow for human exploration. Future inquiries into the Martian shadow phenomenon will delve deeper into its implications for understanding the planet's atmosphere and surface interactions. Advanced satellite missions are anticipated, equipped with cutting-edge sensors that will capture high-resolution images and gather detailed atmospheric data. These observations will enhance knowledge of how solar radiation interacts with Martian dust and ice, revealing the influence of these factors on shadow formation. Collaboration between international space agencies will likely expand, fostering a comprehensive analysis of shadow patterns across diverse regions of Mars. This interdisciplinary effort will include planetary scientists, climate modelers, and robotic engineers, each contributing unique insights to the complex dynamics at play. As these collaborations unfold, predictive models may emerge, offering valuable forecasts about seasonal changes and their associated shadows. In addition, the development of autonomous rovers equipped with advanced imaging technologies could facilitate on-ground exploration of shadowed regions. These rovers will be tasked with collecting samples and conducting in-situ experiments, aiming to unravel the mystery of how shadows impact surface chemistry and potential microbial life.